It is the classic physics class visual, a single, crisp line of light abruptly pivoting as it hits a block of glass. That crisp line is great for calculating angles, and it tells us exactly what happens. But drawing a one-dimensional ray completely fails to explain why the light is forced to change direction in the first place. To see the physical cause, we have to stop looking at light as a single line and start looking at its true form, a continuous series of parallel ripples, known as a plane wave, moving through space. Refraction occurs because these wavefronts experience an asymmetrical change in speed. One side of the wave hits a new material and slows down, while the other side is still moving at full speed, forcing the entire wave to pivot. To prove Snell's law mathematically and understand how light actually propagates, we must permanently abandon the single ray and track the geometry of the entire wave. This exact problem sparked a massive scientific debate. In 1637, Isaac Newton championed the corpuscular model, arguing that light was a stream of particles. His math worked, but it required a strange assumption. For light to bend inward toward the normal line, those particles had to speed up when they hit a denser material like water. The Dutch physicist Christian Huygens argued the exact opposite. He proposed a wave theory of light in 1678, which demanded that light must actually slow down to create that same inward bend. Huygens suggested that every single point on a wavefront acts as a tiny new source of secondary wavelets spreading outward. The forward envelope of all those overlapping ripples creates the next main wavefront. Despite the elegance of this idea, the scientific community largely ignored Huygens' treatise for over a century, entirely because Newton's reputation was so overwhelming. The mathematical proof we are about to walk through is the exact geometric logic that eventually dismantled Newton's particle theory and firmly established the wave nature of light. The order distance, a to e, equals velocity 2 multiplied by time. Because point A covers less ground than point B in the same amount of time, the connecting wavefront between them, the line from C to E, is forced to tilt. The wave has officially pivoted. We can translate this physical pivot into hard math by isolating two right-angled triangles that share a common hypotenuse, AC, the incident waves triangle, ABC, and the refracted waves triangle, AEC. Using proves the angle change, but equations can sometimes obscure what is actually happening to the physical light wave in three-dimensional space. We established that as the wavefront crosses into the denser material, its forward velocity drops. Because the front of the wave slows down, while the back of the wave is still traveling at full speed, the physical distance between successive wavefronts compresses. The waves literally bunch up against each other. This distantial change of a light beam is not an arbitrary optical rule. It is the direct visual byproduct of the wave being physically compressed and tilted by the resistance of the new material. If both the speed of the wave and its physical length are decreasing, what happens to the frequency of the light? Frequency is strictly a property of the original light source. The number of wave oscillations arriving at the boundary interface every second must exactly equal the number of oscillations leaving the boundary. The rhythm does not change. When light refracts into a denser medium, its propagation speed decreases, its wavelength decreases, but its frequency remains absolutely constant. This specific combination of traits, that light must slow down and compress to bend inward, was finally verified by Foucault in 1850, when he successfully measured the speed of light in water and found it was indeed slower than in air. Huygens' principle took a confusing optical illusion and locked it into a predictable geometric reality, laying the groundwork for James Clerk Maxwell to eventually prove that these ripples were actually transverse electromagnetic waves.